So today we will continue our discussions on the SRAM's stability. So first of all, we will talk about the static analysis. So here static means that the noise will be there for a long time. So actually this is a worst case scenario analysis. And then we will talk about the butterfly curve and then the N curve. So those will define the static noise margin. So we have seen the butterfly curve before, and for the inverter 1 and 2, if you draw the VTC curve, and then the relationship between the Vn1 and Vn2 will form this butterfly curve. So here we have 3 stable points, right? And then we know A and B are the truly stable points. C is the metastable point. So here, if you assume that noise is added to those two storage node voltage, then if you have the noise added, the VTC curve will shift. So here we define the largest square that you can fit between those two curves. And then the largest square, of course, depends on the diagonal length. But then when we define the static noise margin, we look at the side of this square. So this is a SNM, static noise margin, for the hold condition. And we talk about how to calculate the SNM, and you may have homework on that. So here, the trick is to rotate the axis by 45 degrees C. So here, if you do that, then you look at basically the distance between those two VTC, and then you project that to this rotated axis. So you will get this. That is the difference. Let's say this point to this point. So you look at the largest distance here. That will be the diagonal of this square. And then this D1 divided by square root of 2 will be your static noise margin. So this is for the rate. This is for hold. And then we will talk about the rate, which will be new. So the rate condition will be worse than the hold condition in terms of the noise margin. So why is that? Because during the rate, you know that the pass gate is turned on. And then the storage node, for example, we talk about that N1 node, voltage will be disturbed a little bit. If you recall the voltage divider effect we discussed earlier. So the storage node voltage will increase a little bit. That will reduce the static noise margin. So here, there are some early discussions by those papers. You can refer to those literature. And there are like analytical equations derived for the simple case. Of course, assume some, simple transistor model. So let's look at the butterfly curve again. So this is the hold condition. We see this before. So here I just want to emphasize that you can define two square, right? Because you have two branch here, right? Because 45 degrees C, then this is mirrored. So this two curve will be symmetric respect to the 45-degree line. Only when those two transistor, let's say the two branch are identical. If there's mismatch, due to the process variation. Then the static noise margin L means here SNML and SNMR, the left and the right, will be different. If there is a mismatch, for example, in the transistor's threshold voltage, then you will have two square, okay? So here we define the smaller one as the static noise margin because we want to account for the worst case. So the smaller one of those two will be the static noise margin. Okay. So this is again for the read, for the hold, and then we'll talk about the read. So here you see this is a read butterfly curve. It's different now. And compared to the hold, you see that the square here you can fit shrink in terms of size. So why is that? Okay. So here, if you look at the red curve here, used to be like this, right? Used to be like this for the hold condition. But now for the read, this is hold. Now for the read, the lowest level of the Vn2 is above 0. This is above 0, above GND. So why is that? Because again, this voltage divider effect, right? So this Vn1 or Vn2 doesn't matter. So they are equivalent, right? So this voltage basically, if you look at Vn1, that is here, also above 0. This is because this voltage during the rate is larger than 0. So how do you get this kind of rate butterfly curve? Actually, this will be your homework. So I will give you some hint. When you analyze this circuit, you can always just look at half of that, right? Because the other one is just mirrored along the 45-degree line, assuming they are symmetric and matched. But of course, in the real circuit, maybe there's mismatch. But anyway, so you look at half of that circuit. Let's say you have 3 transistors here. Then from those 3 transistors, you should be able to draw this butterfly curve, even in the read condition. Okay. So the read condition here, if you recall, your bit line will be precharged to VDD. And in the static analysis, we will assume the bit line kept at VDD. Okay, in the static case. But of course, in the dynamic case, you know that the bit line will decay, right? Depending on the data pattern, if here is 0. But for the static, okay, let's assume the bit line is always VDD. Then the butterfly curve really means that you are looking at the relationship between this input voltage and then this output voltage. Or let's say this is your Vn1, this is your Vn2. So you are looking at the relationship between those two load voltage. So what you need to do here is to ramp the inputs, let's say Vn1, from 0 to VDD, 0 to VDD. So you ramp up this voltage, okay, Vn1, which is input from 0 to VDD. And then initially, if this is 0, then you store 1 here. So then the Vn2 will respond from the VDD and then down to some level. But the lowest level won't be won't be zero for the rate condition, because here you still have the current flow this way. So this lowest level will be decided by the voltage divider effect between the pass gate and then the pull down. Right? So that is the lowest level. So in your homework, you will, solve this circuit using the, for example, Kirchhoff law. And then this circuit, all the three currents through those three transistors, when you add up, will be zero. The net current is zero. If you follow this principle, you should be able to draw this VTC curve. Okay. Right? This is how you get the red curve. And then you can mirror that, then you get the blue curve. So you get this distorted butterfly curve for the rate condition. So any questions here? Okay. So this is just a summary here. The rate SNM will be smaller than the hold SNM because this will be a worst case. So if we didn't specify read or hold condition, when we talk about the SNM, by default, we will mean it's read SNM because it's worst condition. So here, if you look at the device design parameters, that may affect the SNM. What matters here is this beta ratio. We discussed that before. So that is the W over L of the pull down divided by the W over L of the pass gate. If we have a larger beta ratio, we can pull down this voltage closer to the ground. So that means here the lowest voltage will be, if you increase the beta value, then your butterfly curve will become like this, right? So this will get closer to the ground. That will enlarge the square you can fit into this butterfly curve. That will increase your static noise margin. And also this beta ratio, if it's larger, then this slope, the pull down slope will be steeper. That will also help to enlarge this square. So if you want to maximize the static noise margin for the rate condition, you want to increase the beta ratio. Of course, at the expense of larger silicon area, because now your pull down transistor becomes so large.
Will increasing the size also affects the lowering of voltage at bit line? Like, will it take more time to create the delta V?
Actually, not necessarily, because if you increase the size of the pull down transistor, then of course, the limitation might be your pass gate, right? Because the speed, how fast you can discharge the bit line depends on the current flow through this pass. It's like two resistor. You increase this increase the, let's say, conductance of this guy. You still, reduce the overall resistance, right? Your bit line discharge will become faster. So, but still, your limitation might be the pass gate channel resistance. Okay. So then here we have done some simulation using some 28 nanometer transistor model. If you, change the beta ratio, let's say from 2 to 3, you see that the static noise margin improved by like 60 or 70 millivolts. And here we sweep the VDD. Again, the VDD by itself will also determine the static noise margin, right? Because here the starting point is your VDD, right? if your VDD is smaller, let's say start from here, then of course your square will be smaller. So the VDD matter, okay? The beta ratio matter, right? So here you see that as we lower down the VDD, then the noise margin will shrink. But if you increase the beta ratio, then you can improve. This is simulated by the SPICE with some 28 nanometer transistor model.
So, is there any limit to which we can increase the VDD? Like we are stopping at 1 volt, but if we go beyond, will that saturate or?
Yeah, from the trend you see that it kind of saturate, right? But you want to reduce the VDD, right? For circuit design, you always want to reduce VDD. Why do you want to increase VDD? You want to lower the power consumption. You want to reduce VDD.
But I think it helps to increase the noise margin. So
Noise margin, I would say, if you get like 150 to 200 millivolt, good enough. Okay. But below 100 millivolt is tricky. Okay. It's really tricky. Okay, so then we talk about the hold, read, and then the write static noise margin. This is less often discussed, but actually you can define the write static noise margin as well. So here, if you look at the circuit for the write, the only difference is that in the read condition, both bit line and bit line bar will be VDD. But for the write, if you recall, you have to prepare the data pattern. For example, here in this case, you write 0 to the left, write 1 to the right. So then this will be your bias condition. And you can also analyze 3 transistor as a group, right? The left 3 and right 3. And then again, what you want to do is with those bias condition, 0 VDD, and here your ground. If you sweep the voltage Vn1 and Vn2, you will get this kind of curve. So here, if you look at the right group, the red one, those are the same as the read condition, right? So here, the bias condition is the same as the read. So that's why you have this VTC curve, like the read. And then the lowest one is not 0. This is the same as the read condition. But if you do that for the left 3 transistor, now the difference is that here, this voltage, this bit line voltage is 0. So if you sweep the Vn2 and then you try to get what is the Vn1, then you have this curve. Okay. So here, you see those two curves will only have one intersection. That is this point. Because you want to write the data in, you want to deterministically flip the data pattern to be this point, which means Vn1 is 0. Right? This point is Vn1, 0, and then Vn2, 1. This is the same pattern as what you want to write in. So for a successful write, you want this one to be the only intersection between those two curves. That's why you define the noise margin for the write is the here smallest square that you can fit between those two curves. So here this distance matter. Because if there's noise somehow, for example, this one shift, then it may intersect with this curve at somewhere here. Then your write is kind of random. It's not deterministic. So that's a failure for your write. So that's why you want those two curves to be separate. And then you define this distance of course, the diagonal divided by square root of 2. Then the side is your W SNM. Okay, any questions here? All right, so then let's continue. So far, we talked about the butterfly curve and use that to define the static noise margin. But in practice, there's another way to look at this static noise margin. So this is called the N-curve testing method. This is also compatible with the inline tester, which if you characterize the SRAM array, you can measure that on the wafer. So let me just show you what is this N-curve, okay? But why do we need the N-curve? Because here it says that butterfly curve only give you the voltage noise margin. It didn't talk about the current noise margin. So if you want to get the current noise margin, then you will need this N-curve. Okay, so this is how is it measured. So what you will do is that you will attach a probe to this internal load with certain voltage source. So here you have this voltage source attached to the storage node here. And then here you are going to sweep the V in, this voltage, from 0 to VDD. And then you measure what is the current flow in or out from this voltage source. So you are looking at the relationship between the I in versus V in. So if you do that for the rate condition, so this is for the rate condition. So here bit 9 is attached to the VDD. And this is static analysis. So this will be kept at VDD. So if you do that, then this is how it look like. The V in, if you sweep from 0 to the VDD, then the current will actually behave like this. So this is similar to N, the letter N. So that's why it's called N curve, okay? So let's look at this circuit. When the input voltage is small here, for example, 0 volt, 0, start with 0. So here, this pass gate transistor is on, right? So you have VDD here, then the current will flow. And this current will sink to all the current will sink to the voltage source. But then the current will flow the other way. So that's why here the I in is negative, because all the current will flow this way. But by definition, then the current will come out from the voltage source. So it's reversed. That's why it's negative, okay? But as you increase the in voltage here, then this current will be split between this here and also the pull down. So as you ramp up the voltage, less and less current will go through the voltage source, but more and more current will go through the pull down. So that's why here then the current will become smaller in terms of the absolute value. And then at certain point here, then all the current will go through the PD instead of the voltage source. So that is this point. And then if you further ramp up the voltage source voltage, then you will inject current into the node, right? Previously, you sink the current. Now, if the voltage keep increasing, then you inject the current to the node. So that's why the current become positive. So at a certain point, if you inject the current too much, this node voltage is too high, then that will trigger the flipping, because this voltage is too high, then it will trigger the turn on of the other side. So then this will discharge, and then this will be pulled back. And then it will bounce back. And as you approach final destination, which is VDD, if this becomes VDD, then the current will become 0, because here VDD, then the other side is kept at VDD, then no current flow. Okay. So this is the process. But here we are going to define the static current noise margin as the maximum current you can tolerate before you trigger this flipping. So this current value will be the static current noise margin. And then here from this point to this point, we can define as the static voltage noise margin in this N curve, which will not be exactly the same as the static noise margin in the butterfly curve. But later we will see the relationship between those two. But for now, here we define the current, and also we define the voltage noise margin. So here we can take a closer look at those critical points. So here, the point B, we go through this process A, B, P, C, D, right? So at point B, this actually is determined by the beta ratio, right? Because at this point, right, it's basically there's no current going through the voltage source. So all the current will go through the PG and PD. Then this returns to the voltage divider circuit, right? And then this voltage will be determined by the beta ratio. If you have a larger beta ratio, you can imagine then this will shift to this way, right? Then your N curve will become something like this if you have a larger beta ratio, right? So that will increase your voltage and also current static noise margin if beta ratio is larger. And then here, this peak is the other side starts to fall below 1. So this peak will trigger the other side to flip. So here, you can even define the maximum power static noise margin. If you use the current multiplied by the voltage, then you can define what is the maximum power you can inject to this node, to the storage node, before you trigger the flipping. So if you want to really dive into the details of this process, you can look at the traces of the 3 transistor. Because here we have the pull down, cascade, pull up, the 3 transistor. They have the output characteristics, right, like this. So for the pull down and cascade, they're NMOS, so they have this ADVD like this. And for PMOS, we just draw it the other way, because PMOS, negative, and then current negative. So as you go through the A, B, C, D, this process, so you can look at the trace. For example, pull down, initially current is 0, but as you increase the V-in voltage, the pull down, as I said, more current will go through the pull down. So the pull down current will increase until you trigger the flipping, and then it will return like this. And you can do the same analysis for other transistors. I will skip that. And pull up will only work at the later stage. And then pass gate initially start from here. Pass gate voltage current will decrease. So if you combine those three transistors in the same plot, so you will have this three curve, right? This red, green, and this yellow three curve for the pull down, pass gate, and pull up. If you plot those three together, as we change the voltage, input voltage from 0 to 1, this is how it will overlap. But what matters is that those three transistor currents, when you add up, okay, you will get the black curve. That is the current going through the voltage source. Because at this node, right, you have three currents, PG current, PD current, and then PU current, and then you have this I-in current, right? You know the Kirchhoff law, right? So those four, when you add up, will be 0. Or in other words, the input current will be a sum of those three from those three transistors. So if you do that, then you will get the the black curve here, which is the N curve. Okay, a little bit complicated, but if you go through the process, then you will have this. Or if you want to have a try, then if you get access to the spice and then you use some transistor model, you can simulate this by yourself. Okay, any question? So you may wonder, okay, what's the difference between the butterfly curve and N curve? Actually, those two are correlated. First of all, both are static curve. That means, okay, again, a bitman and bitman bar will be kept at VDD. You will attach them to static voltage bias, okay, which is not true for real operation, because real operation we are going to pre-charge the bitman and then we disconnect the bitman from the voltage source. So you let the bitman floating in the real operation. But here for this static analysis, you are going to attach bitman to the voltage source, which is a constant bias. So here, the butterfly curve, because we do not have this additional voltage source. So the sum of those three transistors current will be 0, will always hold. And then the static noise margin is defined as the noise between the two storage nodes. You are looking at the relationship between those two storage nodes. This is more relevant for transistor mismatch. If you have the VTH difference between those left branch and the right branch, you will notice the butterfly curve will be also distorted. And N curve here, because you have additional current from this voltage source. So this equation only hold at those 3 points. Where the input current is 0. So this is more relevant for the noise current injection, if you want to quantify the current. But those two actually can be aligned in this plot. So here, if you plot N curve and the butterfly curve together, let's say the N curve, you look at the left axis, which is voltage, okay? And then the N curve, you look at the right axis, which is the current. So here, those 3 critical points actually are aligned. For example, this, turning points actually aligned. And then you see that the definition, right, will be a little bit different. The static noise margin from the butterfly curve will give you this noise margin. But then from here, you will overestimate a little bit, right? But then from the N curve, you do get the current noise margin. Any questions here?
You explain how encourage the noise between single movement. Is it because we are testing?
Yeah, because you are testing from this to the ground. And butterfly curve, we are testing between those two, right? The relationship between those two. N curve, you are looking at this and here, right? You are injecting the noise this way.
Would it be different if we tested at the one?
One node, I think will be similar, yeah. But one node, you have to apply the voltage the other way. You want to discharge from that node. So here, for the zero node, you want to inject the current. Okay, so which one is better? So fundamentally, they are equivalent. Both are static analysis, okay? And just different ways of mapping. So the butterfly curve, as we discussed, you are looking at the voltage of those two storage nodes. But the N curve, you will look at the relationship with the inject current to the storage node. So I think this is what we already discussed. The butterfly curve is the noise between those two storage nodes. And N curve, here it says more suitable for inline testing because you do not need to do the math to find the maximum square from the measured data. So you do not do the post-processing. As we showed you earlier, you rotate it by 45 degrees and then do this post-processing. So for the N curve, you can directly read out from this plot. You can read out the current and voltage. You don't need to do the post-processing and try to find what is the maximum square. So in terms of the data processing, it will be a little bit easier. Okay. Any questions?
When we take the margin, when we take the voltage margin from the N curve, so again, like in the butterfly curve, we had a left margin and a right margin. But in the N curve, we have like two places which are deviating from zero.
So here we are looking at this at zero load, right? We just here this one is related to the zero load. How much current you inject to the zero load, then you flip that pattern. So that's why you only have one. But we just discussed. He asked what do we do with one node, right? You can do similar thing, but you have to reverse the voltage direction to extract the current from that node. And you can do that, then you get the other one. Yeah. Okay, so then let's look at some real data from the silicon. So here are the butterfly curve measured at 65 nanometer CMOS. And at that time, the SRAM cell size is about 0.6 micrometer square for one cell, 6 transistor. And at that time, the VDD is about 1.2 volts, okay? And then you see that as you shrink the VDD, then the maximum square you can fit will shrink. And here you see the static noise margin is about like 300 millivolts to 200 millivolts. This is from almost 20 years ago when the community was, developing the 65 nanometer technology node. And then this is 45 nanometer. And again, so most here this is read, okay? This is read, I have to emphasize. because as I said earlier, by default, we're going to look at the read because that's worse than the hold condition. So if you read, you are okay, then for sure hold you are okay. So here 45 nanometers, then you see that you always vary the VDD and check how the static noise margin shrink with the VDD scaling. And then 32 nanometer, again, here we show butterfly curve on the left, but in this paper, also the N curve is measured. You see that. And then this is at different VDD, okay. And then it says that at 0.8 volts, the static noise margin is about 220 millivolts in this case. And then the cell size already decreased to like 0.12 micrometer square. And then we keep scaling, right? 22 nanometer. And then here the cell size. You want to remember this technology node 22, because at that time, the SRAM cell size is about 0.1 micrometer square. 0.1 is at 22 nanometer node, okay? And then static noise margin at those VDD, from 200 millivolts down to like 150 millivolts if you keep shrinking the VDD. Because as you scale down technology node, we reduce the VDD. And then this is a 16 nanometer. It's already FinFET. And here we show a group of curves because here we measure many devices. So you will have the statistics due to the process variation mismatch. So if you measure the SRAM array, you will get a group of curves instead of a single curve. You get a single curve from one cell, but if you measure like kilobits or tens of kilobits, then you get a group of curves. So here, this is a 10 nanometer node. And you see the cell size already decreased to 0.03 micrometer square. And then the VDD shrink to like 0.6 or 0.7 volts. Then the static noise margin keep decreasing to be approaching like 100 millivolts. And then this is a 7 nanometer FinFET. So you see keep decreasing. And this is a kind of new data, 5 nanometer. So here, if we plot different technology node together, you will see the trend, right? So first of all, the VDD decrease. Therefore, you see the square become smaller and smaller. So the noise margin continuously decrease with scaling. That's a challenge for the design. Any questions? Then we will talk about some design tricks to improve the noise margin in today's advanced technology nodes. In the following few slides, we'll talk about how to improve. But before that, you need to understand the fundamental conflict between the read and the write operation. The SRAM cell fundamentally, have this conflict. Why is that? Because for the read condition, what you want to do is you want to read out the data, but you do not want to flip the data, right? So in other words, you want the cross-coupled inverters to be strong. And then you only add weak cascade to detect the data. So here we say large and small in terms of the W over L, or let's say the strength, let's say strong or weak. So ideally for the read optimized system, you want the data to be stable. You do not want the data to be disturbed. So you want the cross-coupled latch to be strong. And then you only detect the data through a weak passgate. In the peripheral circuit, you also want to increase the size of the sense amplifier's pull down to read out the data fast. But for the write, it's just the other way around. The write, you want to change the data. So you want this storage node to be coupled to the outside, which means bit line, strongly through a strong passgate. And then you want the internal latch to be weak. That means they're easy to flip, right? You want to write the data easily. And also you want to strengthen the write transistor and write drivers W over L to provide more current to write. So, here the conflict really happens because of the shared passgate. The reason is the passgate is shared, right? For read, your current goes through the passgate, but you want the read current do not change the state. For the write, you also go through that passgate, but you want the passgate to provide enough current and then do change the state, right? This is fundamental conflict because the passgate is shared. So any questions here?
The deoptimized system, why is the write driver small? That doesn't let them touch.
Relatively speaking, right? You want the read to be peripheral circuits or the read to be stronger, right? Relatively speaking. Okay, so then because we have these challenges and this fundamental conflict, so there are many circuit design techniques to increase the stability. So we can classify that into two categories. First one is to modify the supply voltage or the voltage pulsing scheme. Okay, how do you apply the voltage to the VDD, to the bit line? That could help. And there are different papers here listed here. And we will discuss some of them in the next few slides. And the other category is to change the SRAM bit cell design from the fundamental 6 transistor 6T cell to other kinds of bit cell with more transistors. For example, 7T, 7 transistor, 8 transistor, even 10 transistor cell. So you can decouple some of those read and write conflicts. So you have some homework to review some of those papers, and then you will understand some of those techniques. But let me introduce a few widely used scheme. For example, for read, if you want to improve the read margin, so here this is one commonly used read assist scheme. That is to lower the word line voltage. Okay. So that means the word line voltage will be lower than the VDD. So previously, the word line voltage will be the same as VDD, but now this word line voltage is lower than the VDD. So why would this help? Any idea?
So basically, you decrease the VTH to make the passgate weaker.
VTH will not be changed, right? Transistor.
I mean, the purpose is just to make the passgate
Weaker. Yeah, so you make a cascade weaker, right? So the current that you flip, you go through the cascade will be weaker, right? Because the VDD for the, let's say the gate voltage for the cascade transistor will be lower. So relatively speaking, the cascade become weaker. This is what you want, right? If you recall, you want the strong pull down and then weak cascade. So even use the ratio like 1:1, right? The PD over PG 1:1, it could work, right? Because you use different voltage here. Even from the sizing point of view, they're the same, but the current will be different. Or let's say the current drivability will be different. So here shows some data. If you lower the word line voltage by 100 millivolts, you can boost the noise margin by like 50 millivolts.
Case ID will reduce.
Yes, you will have trade-off, like the read speed. Yes. There's no free lunch. Okay, so write assist skin. That could be different, right? Skin. But if you understand the fundamental reason behind this, you could understand this easily, right? For write, what do you want? PG and PU and PG, right? You want what? Strong or weak? Right? So then how do you make this strong, right? You can here lower the bit line voltage to negative potential, right? Previously, when you write 0, you provide this ground. Now, when you write digital 0, you provide a negative delta V, like negative 100 millivolts, 200 millivolts. Then that will effectively increase the VGS of this, not VGS, I mean VDS of this transistor. So basically, the cascade will become stronger. You have more current flow in. That will help you to flip. And then the other trick is to lower the VDD for the cell by delta V, right? Then that means you are going to make the pull up here, this one weaker. So here word line will be kept at VDD, but then the supply voltage for the cell will be lower than VDD. Then you make this pull up weaker. So those will improve the write margin. So if you understand the fundamental reason behind that, we'll always talk about that PD over PG over PU, right? If you know which one should be stronger, which one should be weaker, then you can understand the reasons behind those skins. And here another technique called read, modify, write. Actually, I think you will have homework on this one, read the paper. But let me quickly summarize for you. So this is to address the challenges in the SRAM array. Previously, we only talk about one cell, but actually you need to think about the SRAM array. In the SRAM array, you have many columns, but some columns are not selected. So you have selected column, which means you are going to, your address is going to select this column. You are going to operate on this column, either read or write on this column. But then you have many unselected columns, okay? Because you only select a certain number of columns depending on the I/O width, how many bits you operate. Right? Maybe you operate 8 bits at one time, but your array is 128 columns. So here, then there will be a conflict between the selected colon and unselected colon. Why is that? Right? If you think about this, so for the selected colon, if you want to write for the selected colon for this cell, we haven't talked about the dynamic analysis, but you can imagine if you want to write, you want the right verlan pulse to be long enough to change the data. So this right verlan pulse should be long enough. But then the unselected cell will also see this long pulse. That may unselected cell actually will be more like a read condition. So this long pulse may flip the unselected cell. So for unselected cell, you want to see a short pulse. So that's the fundamental conflict. So how to avoid this conflict? So what you may want to do is read before write, and then rewrite from the buffer. So to summarize, what you want to do, if you want to write the data, let's say here, here we only have 2 columns as example. So for example, this data is 0 and 0 initially. Now you only selected this column. You want to write the data 1 here. You do not want to write, you do not want to change this one. So what you will do is to first do not do the write operation. First you do read this row. So both 0 will be read to the buffer outside. And then your new data come in. You replace this 1 with 1. And then you write the data back. Both 1, 0, 1, 0. You write it back. Okay. So you read and then rewrite. So then because you do the same operation along the word line, of course, you sacrifice the speed. You have to do 2 steps. But then the entire word line will see the same operation at each step. Either you read the entire word line or you write the entire word line, right? There's no difference between columns. Otherwise, different columns, some of them, you want to write, some of them you want to hold, or you want to read, then there will be conflict. Okay, so this is read before write, or read modify write. It's called RMW. Okay, so then let's look at other SRAM bit cell design. What you can do is to add additional transistors. So this is widely used 8 transistor SRAM cell. I think from the foundry you will get this kind of 8 transistor SRAM cell from the PTK and the memory controller and memory compiler. So here the idea is to add 2 additional NMOS transistor, and then here it attached to one of the storage node. Let's say in this one is attached to N1, N2. This one is attached to N1. Or your Q and Q bar, right? And then you have another select transistor, which is controlled by this RWL, read word line. So you have 2 word line here. You will have more routing, okay? You have this write word line, which is a conventional word line, which controls the pass gate. Now you have additional word line, which control this select transistor. So this select transistor and then this transistor, 2 pass gates, basically, form a discharge path. And then you have additional bit line. This bit line is reserved for the read, so it's called RBL. So here, what you will have is you turn on during the write is the same as before. I will skip the write condition. Write will be the same as before. The difference is now when you read, you will turn on this read word line. And then this transistor will be always on. But whether this discharge path will conduct current or not depend on this transistor, because they're in series, right? So this transistor, if your N1 stores 1 here, then both transistors will be on. This is VDD, right? Then you have 1 here, then you have the discharge current. So then the read bit line, will decay. But if you store 0 from the N1 node, then this transistor is off. So you do not have the discharge path, then your read bit line will maintain. So you create the delta V this way. So this is a read path. Now this read path is decoupled from the write path. Write, you go through the PG, right? So read and write, this is the write path. Is decoupled. This solves the fundamental conflict we discussed earlier, right? Now you can optimize the read and write separately. So if you want to read faster, then you size up those 2 transistors here, which will not affect other like write gamma ratio for those PG and the PU there. So it's totally separate. And also here, because you get the static voltage from this N1 node. So in this case, the static noise margin, the read, will be the same as the hold. Why is that? Because here the read will not impact the other side. During the read, actually this red word line is off. So this is off. So here you only have the cross-coupled latch in the read condition. This latch give you a static voltage to this node. So the read noise margin will be the same as the hold noise margin in this case. Right? Any questions? Of course, the trade-off, as you can tell easily, right? So the area increase. You need 2 more transistors. Okay, so then let's continue. Now we will discuss the dynamic stability. So this is more practical, actually. So what we discussed so far, the static analysis, when we talk about the butterfly curve, those are ideal conditions. Actually, will never happen in the real circuit, because in the real circuit, you are not going to bias your bit line to a constant voltage source. That will never happen. So in the real circuit, also the noise will not be forever, right? Because in the static analysis, we assume the noise will be there forever. So the noise usually is very short term in the real circuit. So we need to look at the dynamic stability. So here, if you look at the cross-coupled latch in the hold condition, you can assume there is a noise current injection to one of the storage node, let's say where you store 0. But here you have to assume the noise will be there for a limited time. That means dynamic, okay? So what we will have here, for example, if you hear this current will only stay there for 200 picoseconds. What will happen is that because you inject the noise current to the V2 node, which stores 0, so V2 voltage will increase over time. But now after 200 picoseconds, you withdraw the noise, or the noise is gone. Then the V2 voltage will recover because of the latch, right? It will go through some iteration, and then the voltage will go to the original state. So similarly, you look at what will happen to the N1 voltage. It will decrease for the first 200 picosecond. Now we rotate the X and Y. Now this Y-axis is time, and the X-axis is VN1 voltage. So then you will, initially is VDD, it will decrease a little bit, and after 200 picosecond, it will recover. So if you map those two time waveform to this V1 and V2 plot, it's like your butterfly plot, which means the V1 and V2 relationship. So you will have this trajectory. So because when you map those to this V1 and V2, you'll lose the time information, right? Because you used to have voltage versus time, but if you map this to the voltage only plot, the time information is gone, but the time information will be a trajectory of this point. So this point initially, this is your data pattern. Then this two voltage, N1 and N2, will follow this trajectory, okay, during the noise injection. So this is when the noise is short enough, right? It will recover, okay. But what if the noise is long enough? Here you see the noise now is more than 200 picosecond. So your V2 will keep increasing, and then this will trigger the flipping. So it will, go to the other side. Similarly, here the V1 voltage will keep decreasing. And then now, if you remove at this point, because now it's this trajectory, let's say the trajectory start moving. Even here, now you remove the noise because it already crossed the boundary. It will end up, flipping to the other side. It's a dynamic process here. Depend on the time, and also, of course, depend on the current level, right? You can imagine, right? If you inject the current larger, shorter amount of time, you can accumulate enough charge to trigger the flip. So in the real circuit, you have to think about the duration of this noise. So that's why we have this critical time for flipping, T critical, right? So here, if you look at the trajectory, right? Basically, you want to make sure if this is a symmetric, matched, then 45 degree, right? Because it's mirrored in the butterfly curve, VN1, VN2. So this trajectory, as you inject a noise, then it will move this way. And then if you withdraw the noise before it reach this boundary, then it may come back. But if it go across this boundary, then it will end up with the other side. So the time for this point move from here to here will be this critical time. So here in this paper, it proposes this concept called the separatrix. So basically, it's a boundary, right, between those flipping. If it's a symmetric SRAM cell, ideal case, then this is 45 degree none, right? No matter how you move, this. As long as you do not go across this, after the noise is gone, then you will come back. It's like there is a force to, attract this back. Of course, in the real circuit, then you may have the process variation mismatch, then this boundary will be, distorted. So here, you can use the same concept to analyze the right pulse width. So in the right condition, you intentionally inject the current from the pass gate, right? Now your current is not coming from the noise source. Your current is really coming from outside, from the pass gate. But the same concept apply here. Your pulse width for the right condition, the right word line, pulse should be long enough to make sure that this trajectory, this point, will move across the boundary for a successful write, right? So if your write pulse is too short, then you will not successfully write the data. So that's why here we say that the right dynamic noise margin, okay, depending on here, the right pulse, word line pulse, how long it is. You want to make sure this TW is larger than the T cross, that is the time to cross, or this T critical. So you can flip the data. So here, this is just a comparison between the read. During the read, you want the read time to be short, therefore you do not disturb. And for the write, you want this write time to be long enough, so you do flip. Right, that's why we talked about earlier for the read modify write, why do you need to, separate the two step? Because the word line pulse width ideally should be all different for the read and the write condition. So here, this is very important conclusion I want to draw. So compared to the, let's say this dynamic noise margin, DNM, compared to the static noise margin. So we say that here, the static noise margin is pessimistic for read or hold compared to the dynamic noise margin. And then it is optimistic for the write condition. So what does this mean? So any idea? So in other words, let me ask the question. If from the static noise margin analysis, let's say the static noise margin tell you it's 100 millivolts, the dynamic noise margin for the read, let's say, is higher or lower than 100 millivolts. Right? This could be higher than 100 millivolts. But this is for the, let's say, yeah. And then if this is for read, okay? For write, if this is like 200 millivolts, then your write could be less than 200 millivolts. This is when we talk about the pessimistic or optimistic. Basically, for the read condition, you underestimate the noise margin for the static analysis compared to the dynamic analysis. Why is that? Because in the static analysis, you assume the noise will be there forever. But actually, the noise will be there for only a short period of time. So even the noise, it could be higher than 100 millivolts, but it will be there only for a limited time. So the circuit might be stable, right? But for the write, it's just the other way around. In the write, you assume, okay, 200 millivolts is safe for the static, but actually, if your time, the write pulse is not long enough, your 200 millivolt may not, work safely. So that's why we have this difference. Of course, in the real circuit, you care about the dynamic noise margin. That is more, close to the real operation. So just 2 more slides. I will finish up in 1 minute. So here, very important, Schmo plot. When you look at the papers or even the data sheet from the foundries, you will see this Schmo plot. This tells you because after you fabricate the SRAM array, you will test at different clock frequency, and then you will test at different power supply voltage, and then we'll define the pass and fail depending on the error rates. So here we have this boundary, okay, at different this is a combination of different power supply and different clock frequency. And then here this is pass condition, this is fail condition. But my question is that when you fail here, there are 2 kinds of fail. One is write fail, one is read fail. So my question is, at those 2 corner, let's say here at high clock frequency, at 2 gigahertz, 1 volt, that's the best you can operate. If you want to operate high frequency, you will have to, increase the VDD. But let's say here, if you fail, is it dominated by read fail or write fail? That's the question for you. Any answer? Read or write? Write, okay. This is write fail. Because write, you need enough time to write. If your clock is too fast, then your write fail, okay? Write fail. So here, on the other hand, here, this is read fail. Why is that? Because your voltage is too small, VDD is too small, your read margin is too small. That will be dominated by the read fail, okay? So this is from older technology node. If you look at the latest data from TSMC 5 nanometer, same thing, okay? You will test at different clock frequency and then different VDD. So here you see that at 5 nanometer, you can run at really fast clock, like 4 gigahertz at 0.85 volts for the L1 cache. And for L3 cache, then you, of course, will be slower. Okay, so I think that's pretty much what I want to share today. This is a quick summary. I will skip that. You can read the text. Okay, we'll stop here for today. Thank you. One second.